An amine is an organic functional group composed of a nitrogen atom bound to other groups. And there are 5 important topics to discuss when it comes to amines. Number 1 is chirality, number 2 is basicity, number 3 is preparation, and that has 3 subsections. Number 4 is the Hoffman elimination, and number 5 is the Cope elimination. Number 1, chirality. It turns out that an amine, in its neutral state, is a nitrogen bound to 3 groups. Now, that nitrogen will also have a lone pair of electrons. So if you count the lone pair of electrons as a group, you have a total of 4 groups bound to the nitrogen atom. Now, like a carbon bound to 4 groups, we can consider this nitrogen, this amine nitrogen, to be chiral. However, unlike a chiral carbon, the amine chiral center is going to be constantly interconverting between one isomer and another isomer, the R and the S. And this is called pyramidal inversion. Pyramidal inversion is occurring constantly at room temperature. Specifically, Brown cites a figure of 2 × 10⁻11 times per second. That is way too fast to preserve one enantiomer or another enantiomer. And specifically, the energy needed to get the amine from one enantiomer to another enantiomer is 6 kilocalories per mole. So that is a very low activation energy for this conversion to happen, and thus it is happening constantly. Now, if you were to do the R or S configuration for an amine that you draw in one configuration or another, then you would consider the lone pair of electrons on the amine to be group number 4. Then you would consider the hydrogen to be group number 3, and then you would go up from there, if there's a hydrogen, that is. This is because, if you think about it, a lone pair of electrons will always have the lowest atomic number in the amine chiral center, because it has 0 protons. The second topic with amines is basicity. With the basicity of amines, we often speak of the pKa of molecules that contain amines. When discussing the pKa of an amine, we are discussing the pKa of the protonated version of the amine. If you take ammonia, for example, which is NH3, we're discussing the pKa of NH4+, which is the ammonium cation, not the pKa of NH3, which is not an acid. So it's easier to discuss the pKa of the protonated form, and that is what we do. Now, there are some trends when it comes to the basicity of amines that basically are the opposite of the trends that determine the acidity of an acid, any kind of acid. So there are 5 general trends, and I'll list them out, and then we can go through each one with an example. All right, the first one is resonance. Increase in resonance of the amine decreases the basicity. The second is inductive effect. Increase in inductive effect, which is electron withdrawing via electron withdrawing groups next to the amine nitrogen, decreases basicity. Nitrogen being a pi donor, which means that its lone pair of electrons can be donated into a pi system, decreases basicity. Nitrogen as a pi acceptor, which is where the lone pair of electrons is donated to nitrogen, actually increases basicity. And finally, and very importantly, the hybridization of the nitrogen atom increases its basicity the closer it is to sp3. So the greater the p character and the lower the s character, the more basic is the atom. And this is the exact opposite of the trend that we saw in acidity of any other molecule. So in the acid-base section, one would learn that an alkyne, a terminal alkyne, will be acidic because it has an sp hybridized carbon. However, when it comes to amines, sp hybridization is less favorable for basicity because when you add a positive charge into a more electronegative orbital, like an sp orbital that is electronegative by way of its high s character, it will be less stable than with a negative charge. So, first let's talk resonance and conjugation. And the best way to understand this trend is the difference between something like methylamine and something like aniline. So, methylamine has a pKa of 10.64, which means that it is fairly basic. We do not consider this to be a strong base, but it is fairly basic. A little bit more basic than ammonia, but we'll get to that in inductive effect. So anyway, we're talking about the difference that comes when you have conjugation. Well, let's compare methylamine to aniline. Aniline is the amine that is an amine group bound to a benzene ring. Aniline has a pKa of 4.63. That is much lower than methylamines. A lower pKa means more acidic and less basic. So think of it as the higher the number for pKa, the more basic. The greater the number, the greater the base. So we can see that methylamine is a greater base than aniline, but why might conjugation play a role in this? Well, it turns out that aniline has the ability to resonate the lone pair on the nitrogen that is coming off of the benzene ring, and that resonance happens in the benzene ring. So when you donate the lone pair into the ring, you are essentially taking it away from the position it would need to be in to do an attack of a proton of an acid and to basically perform the function of a base, which is to attack a proton. So aniline has its lone pair all tied up in resonance and is less likely to attack a proton. Well, then methylamine, it has a lone pair as well, and it's amine, and that's the amine lone pair that needs to do the attack, to be a base. So with aniline, your lone pair is tied up in resonance. It's busy, essentially. So if it's busy in resonance, it's not available to be a base. But with methylamine, that lone pair is perfectly able to act as a base. And it does, which results in its increased pKa value compared to something like aniline. And this comparison with methylamine or any aliphatic or saturated amine can be done with any non-aliphatic amine, such as a heterocycle like pyridine or imidazole. Now, these other amines, pyridine and imidazole, those have conjugation. They have resonance. And they are all going to be less basic, which means a lower pKa value than our methylamine or dimethylamine or ethylamine or cyclohexamine. All of these aliphatic amines are going to be stronger bases than all of the conjugated amines. The second important trend is the inductive effect. Now, there are two kinds of induction you can have. You can have electron donating inductive effect, which I suppose we would call actually hyperconjugation. So if you have more methyl groups, you have more electron donating effects because that carbon is slightly more electronegative than the hydrogens in the methyl groups. But the opposite occurs when you have an electron withdrawing group, such as a chlorine, fluorine, iodine. Now, when it comes to amines, we want more electron donating groups if we want a more basic amine. So ammonia versus methylamine. Methylamine has a methyl group attached to the nitrogen. That methyl group is donating electron density to the nitrogen, and that increases the basicity of the nitrogen because the more electron density it has, the easier it is to reach out and grab a proton. Now, this can be generalized to any sort of electron donating group. So say you had an amine with an OH nearby. That would donate electron density to the nitrogen, and it would make it more basic. And we could also talk about the inductive effect in terms of putting electron withdrawing groups, like chlorine or fluorine, or oxygen. So Master Organic Chemistry gives the example of piperidine, which is a nitrogen cyclohexane, with morpholine, which is a nitrogen cyclohexane with an oxygen directly across from the nitrogen. So 6-membered ring, you have nitrogen, then you have an oxygen, ether sort of thing across from the nitrogen. That oxygen is going to do electron withdrawing. So it is going to remove the electron density from our nitrogen and remove, in turn, its ability to grab a proton, which is what it does as a base. So the more such electron withdrawing groups you have near your amine, the less basic it will be. Now, how about number 3, which is nitrogen as a pi electron donor. So this is sort of the same trend as with resonance, although we could say that there's a special kind of resonance that occurs when you have something like a carbonyl nearby. So a carbonyl bound to an amine is also known as an amide, which is a carboxylic acid derivative. Now, the thing that makes the nitrogen on an amide not basic is the resonance that it does with that carbonyl. Specifically, the resonance in which it donates its lone pair to oxygen, and oxygen becomes negative, nitrogen becomes positive, and you lose that nitrogen's ability to reach out and grab a proton. So amides are not basic, and that is because they are pi donors. Master Organic Chemistry gives a few examples of good pi accepting groups that are going to decrease the basicity of your amine. So that's something like a nitro group, NO2, a sulfate group, SO3H, or a cyanide group, CN. So these are all going to be electron withdrawing groups via resonance. So they're going to take the amine's electrons via resonance, form a double bond with the nitrogen, and make that lone pair less accessible for attack. So the resonance/conjugation effect is sort of similar to the pi donor effect, although it is enhanced when you have a carbonyl or such electron withdrawing group nearby. Now the nitrogen can also accept a lone pair in resonance. So the fourth trend is nitrogen as a pi acceptor. And there are only a few cases where this is relevant, but they are interesting ones that are maybe important to know due to their testability. So one is this molecule called 4-dimethylaminopyridine, which is pyridine with an amine coming off of it, and it is a secondary amine that is bound to 2 methyl groups. So directly para to the nitrogen in pyridine is a nitrogen bound to 2 methyl groups. Now, that nitrogen has a lone pair on it, and that lone pair can donate into the ring, and we know that when you donate an electron pair via resonance into a benzene ring, the resonance can go para to it. So that para resonance actually goes all the way down to the pyridine nitrogen, and that nitrogen has a resonance form where it has a negative charge. If nitrogen has a resonance form with a negative charge, it is significantly more basic than if it didn't have that. Another very important example is guanidine, which is an NH double bound to a carbon, and that carbon is also single bound to 2 NH2 groups. Now, all of those nitrogens are sp2 hybridized, so you would off the bat say, well, maybe it's a little bit less basic. But actually, it is incredibly basic, because that NH nitrogen has resonance forms with those NH2 nitrogens in which it has a negative charge. And that negative charge is going to go grab a proton. So you have 2 significant resonance contributors in which the NH nitrogen has a negative charge. It is going to grab a proton, and in fact, guanidine has a pKa of 13.6, which is the highest pKa we've discussed so far. For reference, amide, the amide anion, not to be confused with the amide functional group, has a pKa of 16. Okay, so 16 versus 13.6, it's not that far away. I mean, it's not as basic as amide, sodium amide, but that's pretty basic. It's pretty basic. It's the strongest base we saw in class. So important to note, and that is because, again, nitrogen here is acting as a pi acceptor. So you're getting the lone pairs accepted by the nitrogen, which gives it negative charge in some of the negative formal charge in some of these structures. Now, couple of other important bases to discuss. I wanted to mention imidazole, which is a 5-membered ring with 2 nitrogens and all sp2 hybridized atoms. So imidazole has a pKa of 6.95, which is not very basic, but it is more basic than pyridine. Why? Because it has resonance forms where the positive charge can be shared around the ring, whereas pyridine does not have as many resonance forms. It's a slight difference. Pyridine is 5.25 and imidazole is 6.95, but it is significant to mention. So the last trend with the basicity of amines that I mentioned at the top is the trend in hybridization, and it is the opposite with acidity. With acidity, the sp is going to be the most acidic orbital, the sp orbital, but with basicity, it's the opposite. sp3 is going to be the most basic orbital. And why might this be? Well, consider the sp3 orbital. It is formed from the combination of 3 p orbitals and 1 s orbital, which makes it more like a p orbital than an s orbital. Well, then consider the sp orbital. It's bound, it's created by the fusing of the s orbital and the p orbital. Now, if those are 50-50, then you're way more like a p orbital than the sp3 orbital. sp has more s character. You're more like an s orbital than the sp3 orbital. So sp orbitals have more s character than sp3 orbitals, which have more p character. Just look at the number next to the p and consider the characterization like that. So any aliphatic amine is going to be more basic than any conjugated amine because that sp3 hybridized orbital has more p character, in which the lone pair is sort of sticking out farther, and that makes it more basic. So a good example of a very not basic amine due to hybridization is the nitrile amine. The nitrile amine has a triple bond with carbon. The nitrile functional group is a carbon bound to nitrogen 3 times. Now, that nitrogen has a lone pair, yes, but that lone pair is held in an sp orbital. The sp orbital, remember the p character, is much lower. So it is going to be a smaller orbital, and it's going to hold that lone pair much closer in and going to be less able to go and grab a proton. So the nitrile functional group actually has a pKa of -10, which is not basic at all. In fact, it's the opposite. It's highly acidic if you have a protonated nitrile. So be on the lookout for nitriles as a not basic amine, despite how they might look. Okay, so done with the topic number 2 of basicity, we move on to preparation. So the first important thing to mention when it comes to the preparation of amines is how not to prepare them via the SN2 reaction. This is how not to prepare an amine. So we learned that the SN2 reaction occurs when you have a nucleophile and an electrophile, like a haloalkane, with let's say a primary carbon with the halogen. Well, when you put in a nucleophile like water, that'll attack the CH3 group, for example. Like if you had CH3Br, it will attack the CH3 group, Br will leave, SN2 reaction. And it's really better when you have a stronger nucleophile, like maybe another halogen, like iodine. Okay, the iodine would attack the CH3, the Br would leave, that's SN2. Well, what if you did SN2 with NH3? You'd expect a primary amine. But that's not what happens. When you do an SN2, where the amine is the nucleophile, and you have something like ethyl or propyl halide, so like methyl bromide, for example, you actually get a quaternary amine because the SN2 happens again and again and again, and if you add a base to this process, it'll go a lot faster. So a quaternary amine is an amine bound to 4 things and positively charged, because nitrogen with 4 bonds has a positive formal charge. So you have nitrogen, methyl, 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 and that's positive, and then your counterion, well, you just kicked out a bunch of bromines, so you will have Br minus. Now, that is a great way to make a quaternary ammonium salt, but it is not a good way to make an amine, which is a nitrogen that is bound to 1, 2, or 3 carbons. Okay, so how do we make a nitrogen bound to 1, 2, or 3 carbons? Well, The first such method is epoxide opening, which is similar to SN2, except you don't get an endless reaction, because once you open the epoxide, you'll have a nitrogen and then an O minus on the other side. So it is not going to keep doing endless SN2s, so epoxide opening will give you an amine that is 2 carbons away from an alcohol. We could also do reductive amination. In reductive amination, we start with a carbonyl, and then we add an amine of any kind. In the carbonyl and nucleophile substitution unit, we learned that an amine can add into a C double bound to O, a carbonyl, and become what is known as an imine. An imine. So the imine is a carbon double bound to a nitrogen instead of an oxygen. It's like the amine version of a carbonyl. And what will happen in reductive amination is that you make this imine first, and then you reduce the imine to an amine. And in order to do this, you need a weak reducing agent. And there's a specific one that we used in class, which is sodium borocyanate, NaBH3CN. The CN is there as an electron withdrawing group to take a little bit of electron density from the hydrides that are normally on sodium borohydride, which is NaBH4. Another way to make an amine is the reduction of a nitro group that is on an aromatic ring. The reduction of the nitro group occurs when you have an NO2 coming off of an aromatic ring, and the reduction is done via H2 and palladium, nickel, or platinum catalyst. And the result of that reaction, you have benzyl NO2 on the left, and then you have H2 and palladium on your arrow, and on the right you have an amine, an H2, coming off of the benzene ring. Another way to reduce something into an amine is to do it with any of the carboxylic acid derivatives we learn that have nitrogen. So let's start with the amide. So the carboxylic acid derivative amide, as we discussed earlier, is the NH2 bound to a carbonyl, and you can reduce that using lithium aluminum hydride, which is the strong reducing agent that will reduce any of the carboxylic acid derivatives. Now, when you reduce a carboxylic acid derivative such as an ester, an acid anhydride, or an acid chloride, you get an alcohol. However, when you reduce an amide or a nitrile, you get an amine, because there is no oxygen, or it is less favorable for the oxygen to be in our product. So for the nitrile, there's no oxygen at all, so for sure that's going to make an amine when you reduce it with LAH, but with an amide, you're actually going to have that oxygen just leaving. It's going to leave as something, and then you're going to get your amine. All right, so those are some ways to make an amine, but there's one even better way, because all of these ways, they're not as straightforward. They're not as beautiful as an SN2 reaction. So another way to make an amine is to do an SN2 reaction with the azide anion. The azide anion is a nitrogen, another nitrogen, and another nitrogen. It's 3 nitrogens, all bound together, and they function as a nucleophile. Now this is a kinetic molecule. It is not a good base. So being kinetic, it is going to attack SN2 style. If you attack an alkyl halide, you're going to get the azide onto your alkyl chain. And an azide is just one reduction via lithium aluminum hydride away from being an amine. So if you do any SN2s or you add in an azide, all you have to do is do lithium aluminum hydride reduction, and you get an amine plus nitrogen gas, which evolves out of the solution, and you get a great yield there, because nitrogen gas leaving is a very energetically favorable step, and it is also going to help your equilibrium, because nitrogen gas leaving pushes the equilibrium to the right. So moving on now with the amine topics, we've talked about preparation via the azide anion, and that was the main way to make an amine that we learned in the amine lecture. And so now we're on to the last 2 amine topics, which are both reactions of amines. Now, when it comes to the reactions of amines, we're going to focus on elimination, because it turns out you can get a nitrogen atom to be a very good leaving group via certain methods that start with an amine. So we'll start with an amine. Let's say we start with a quaternary amine. We learned how to make quaternary amines just a little bit earlier when you learned that doing SN2 with an amine and an alkyl halide is going to result in a quaternary ammonium salt. Well, if you take that quaternary ammonium salt, which is, picture an N bound to 3 R groups and then a 4th R group, and I mentioned the 4th R group because let's consider that 4th R group like a butyl group, and let's say it's on the carbon 2 of that butyl group, and we take silver oxide, which is Ag2O, and water, H2O, so a slurry of Ag2O and H2O. This will eliminate, first it is going to switch the counter ion from the chloride or bromide or iodide that you had when you had your salt. It is going to switch that counter ion into a hydroxide. But what's the deal with switching out that counter ion to a hydroxide? Why would we do that? The next step is heating. And when you heat a quaternary ammonium hydroxide salt, it will eliminate at the less substituted carbon, aka the Hoffman position. That's why this reaction is called the Hoffman elimination. So, say we have that quaternary ammonium on the carbon 2 of a butyl group, and then we take our hydroxide and add heat. Well, we added the hydroxide by doing Ag2O over H2O slurry, and then we do the heat, and we pick a hydrogen off of the terminal carbon, and we kick out the NH3 or N-alkyl 3 group. But why is it that when you kick out an N and 3 alkyl group, you get the less substituted product? That's because it's very bulky. The N group, quaternary N group, is very bulky, and it is going to hinder any incoming base from attacking at the more substituted carbon position. So it's going to attack at the less substituted, give you the Hoffman product. And that actually, it turns out that that's the case whenever you have a neutral leaving group, and that could be like an N3, an N with 3 alkyl groups. It could be like an SO3 leaving group, anything like that. And that is going to give you the Hoffman product, which is the double bond on the less substituted carbon. Whereas if you kicked out a negative leaving group like bromide, you would get the Zaitsev product, which is what we saw in E2. Unless, of course, you use a bulky base like terpetoxide. Now, that's the Hoffman elimination, and a good way to remember the Hoffman elimination is that Hoffman is the salty elimination. He's very salty, he's mad, and that's why the first step is to switch out the counter ion, the anion, from chloride or bromide or iodide to a hydroxide. So the first step is forming a new salt. So you form the salt, you eliminate Hoffman elimination. Next, cope elimination. We'll say rather than a quaternary amine, you started with a tertiary amine. Now, a tertiary amine, we're going to have some problems maybe synthesizing, because when we learned the SN2, we only learned how to do either like primary or secondary amines, but this is a tertiary amine. Okay, so a tertiary amine is going to just sort of be there, and then we can do something with a tertiary amine. We could do something where we add H2O2, hydrogen peroxide. Now, that is going to form the internal salt, where you have now a negative oxygen bound to your positive nitrogen, which is now quaternary, because you had 3 R groups on your tertiary nitrogen to start, and then you added an oxygen, which made it quaternary. And that is like a Zwitter ion. Then you add a little bit of heat to that, and you get a syn elimination, Hoffman or Zaitsev. And that is because it is actually an internal proton grab that occurs to cause the elimination. So you have the transition state where the nitrogen bound to the oxygen, which probably has a name, the nitrogen bound to the oxygen is going to sort of twist around and grab the proton that is 1 carbon away, and at the same time, it itself, bound to the nitrogen and the 2 alkyl groups, is going to leave. So that is an internal base grab and leaving group leaving. So the cope elimination, just one more time, is H2O2 and then heat, and that is the Zaitsev or the Hoffman product. You only really want to use this elimination when there's only one alkene to be made, either Zaitsev or Hoffman. It is not regiospecific, so you're not going to be guaranteed to get the Zaitsev or the Hoffman, and you usually want to guarantee like that, so do it when there's only one possible option. All right, so to recap, we have discussed 5 topics with amines. 1 was chirality. Amines are chiral, and they're constantly interconverting between the 2 enantiomers. 2, basicity. Aliphatic amines are more basic than conjugated amines. Amines where the hybridization is sp3 are more basic than sp2 or sp. And amines that accept pi electrons from nearby groups like nitrogens, like on guanidine, are more basic than ones that have to give up electrons to a group like a carbonyl. You can prepare an amine. Number 3, you can prepare an amine via SN2 reactions with an azide anion, and you can prepare a quaternary amine with the typical SN2 reaction where we start with a primary amine. For Hoffman elimination, use a slurry of Ag2O and H2O. That gives you the Hoffman product, and that is because you first switch out the salt from the halide anion to the hydroxide anion, and then finally 5-cope elimination, you use H2O2 to do an internal base proton grab, and then you kick out your leaving group, which is a nitrogen bound to an OH, and your 2 alkyl groups. That's all for chapter 23, amines.